Today we're talking about solar sails. You had something you wanted to tell me?
Yeah, I made this picture, made this diagram,
Okay.
and this is how I think a solar sail works on like 1,000 foot level. So I drew a solar sail in red, which is just a straight line,
Okay.
and then there is a tether attached to the solar sail, pulling a payload to the right
Payload is your ship or
using
whatever it is. Okay.
your ship, your people, your cargo,
Okay.
and it's getting pushed to the right in this picture using the force of light,
Okay.
which is that big arrow. And the force of light is generated by the sunlight coming in from the left,
Hmm.
coming in, bouncing off the solar sail, and
Okay.
then that creates the difference in momentum that gets transferred by Newton's third law to the solar sail and then to the payload.
Okay. Sounds good.
Is that right? Is that right?
That sounds exactly right. But you have
Okay.
like little photons bouncing here, however many million per second. Every time they
Mm-hmm.
bounce forward, hit this solar sail here in red, some of them are going to get absorbed, some of them are going to get bounced back, and the ones that get bounced back, well, I guess both of them, they're pushing the solar sail forward a little bit, a little bit.
Right.
Okay.
Yeah. So I think the biggest engineering hurdle for these solar sails um, is the size, because the
Hmm.
force of sunlight is super small. It's not like I can put my hand out in the sun
You don't
and
feel
like,
it.
oh, I feel the force of the sun. I don't feel a thing.
Right, right, right.
So we're pretty close to the sun at Earth distance, and the intensity is pretty high. So you kind of need these huge solar sails to get any kind of big enough force to actually move
Acceleration.
around.
Hmm. Okay.
But I think as far as I understand, the big advantage is your upper limit on speed. There is no upper limit. You could always accelerating towards c
Hmm.
because you're using light itself to do the acceleration.
Right, and you don't have to
So there's
transport your fuel off the Earth. Just
oh
moving
that's
the
right.
fuel off the gravitational well is expensive.
Oh yeah. That's two things.
Hmm.
One is you don't have the fuel. There's no fuel involved,
Hmm.
which is great. You don't have to take it with you. But also like you're always accelerating because you're always approaching the speed of light. Because sunlight can always give you more momentum because in your frame of reference, this light is always moving at c. So
Oh,
you always get forces.
never thought about that.
Yeah.
Hmm.
So
Okay,
some advantages. Disadvantage, it's gonna be huge.
it's got to be huge. How big?
Okay, so that's the calculation that I put together.
Okay, the next over here. Sure.
Uh, yep.
Oh boy. Okay, a lot of
Yeah.
stuff. Yeah, walk us through it.
Yeah. Okay, so starting out some record keeping. So the energy of a photon in general is h nu,
Okay.
which is equal to hc over lambda. So that's Planck's constant times the speed of light divided by the wavelength.
Okay. The wavelength of the. Okay. Yeah, I'm with you.
Yeah. And then the momentum of a photon is equal to Planck's constant over the wavelength of light. So h over lambda.
Okay.
So just put in those there just to remember.
Okay.
And
We'll need
then
them
the
later.
third line is rho reflected. This is some catch-all we have for like the materials in the solar sail. So how well does it reflect light?
Okay.
Uh, and in this, we're approximating. We're going to say 70% of the light is reflected and 30% of the light is absorbed. That's what we're going to say here.
I see. So if I were to move the absorbed from the right side to the left side, it's all the light that's coming in is going to be one, and some of it's
Mm-hmm.
going to be reflected, some of it's going to be absorbed. And if we want to figure out how much is reflected, because that's going to, I guess for whatever reason, we'll see later. And then we'll say that if 30% of it is, of the light is absorbed, then 70% is left over. That's reflected.
Yeah.
Okay, sure.
And so this will
But
enter into our calculation.
this is
The
like
more
a
reflected,
this is like a guess number, right? This is like a
it's a guess. Yeah.
okay.
And I think I heard this from windshields in cars.
Ah,
70% of
yeah.
the light goes through the windshield. So I was like, 70% of the light's reflected by a mirror. Sure.
Okay.
But
Sure.
total guess.
Sure.
But we can mess with that number to change our numbers, but I don't think it ultimately makes the numbers like way different if we change this number.
Let's leave it as
Um,
an assumed number for now, where we could change it later on. We'll see.
yeah.
Okay. Okay.
Okay, the next one is this little n. We're going to
Okay.
call that the number of photons incident on a solar sail per second. So
Okay.
how many photons hit the solar sail per second?
Okay. Sure. Sure.
Just a number. Yeah. And this little n will be equal to the intensity of the sunlight
Okay.
hitting the solar sail times the area of the solar sail divided
Okay.
by the energy of the photon. And the reason that makes sense is the intensity of the sunlight is a power per area.
Okay, so yeah, energy per second
Yeah.
is power. That's a watt. The energy is a
Mhm.
joule per second. That's a watt. And then
Mhm.
divided by area, you get a watt per area. Yeah, that's an intensity.
Mhm. Yeah, so it's how much energy passes through an area per second
Okay,
via light in this case.
I see. And
If we
then if you,
yeah,
okay, I got you. Yeah,
yeah,
I'm catching
yeah,
up with
yeah,
you.
yeah,
Okay, if you
yeah, yeah,
multiply
yeah.
then by the area, you cancel out this area, you get the energy per second. If you
Mhm.
then divide by the energy of the photon, you then
Yep,
get the photons per second.
exactly.
I see. And then with
And
the
you got to
number of
count per
photons, you're
second.
gonna count the momentum. Okay, I see where you're going. Okay,
Right,
please continue.
right. Yeah. So then last thing is big N is the total number of photons. So total number of photons hitting the solar sail uh, in some given amount of time.
Okay, sure.
Okay. So starting off with Newton's laws, force equals dp dt.
The momentum.
So yeah, that's the change in momentum per time is
Okay.
equal to force.
Yep. I'm with you.
And we approximate that as not a derivative, but choose a chunk of time, find the change in momentum of the photons, divide by the time, and that's approximately equal to force.
Sure. Yeah, we don't need to
Okay.
be infinitesimal. This thing's moving.
Right.
Yeah, in space,
Yeah.
macro scale. That's
We,
fine.
we can do it. Yeah, we can do it second by second. That's fine.
Sure. Okay, I'm with
And
you.
then yeah, next line is the only momentum change of the solar sail is due to the photons. There's no other momentum changes.
Okay.
So the change in momentum of all the photons due to the solar sail divided by t gives
Okay.
us the force on the solar sail. If the change in momentum of the photons is one way, then the force of the solar sail has to be the opposite direction. So that's the negative sign.
I see. So this negative is for the change of momentum is the photons are changing in the backwards direction, which means the force is going in the forward direction. So it's a negative overall.
Right.
You just sucked it out. Okay.
Yeah.
Okay.
And then next line, the total change in momentum of the photons over this particular time. Just we can do an individual momentum change of a photon and then add up all the photons.
I see. You do a summation.
Yep.
Okay. Yeah, I'm with you.
Yeah. Next line, we'll do a physicist thing and just drop the minus because we just know we're just looking for force.
Yeah. So we're getting the magnitude, and then the direction of the force is clear. It's the opposite direction of the light. Okay, I'm with you. Not a problem.
And so we need to sum up all the photons. So that's
Okay.
total photon count
Okay.
times. So the sum of all the photons is the total photon
I
count
see. Total photons. Yeah.
times the number absorbed
Okay.
times the momentum plus 2 times the number of reflected times momentum. So where does that come
This
from?
isn't the number. This isn't the number anymore, right? This is like the material properties. Wasn't that right?
Right.
Okay.
Right. So so this is so n is the total number of incident photons.
Mm-hmm.
And then rho says, I think we said 30% are absorbed.
Okay.
So 30% of the n are absorbed, which contributes 1 momentum change to the solar sail.
Okay.
Because the momentum of the photon comes in, gets absorbed by the solar sail. So its momentum goes from momentum to 0. So it contributes 1 momentum.
I see. So if I catch a baseball in my glove, I've sucked up the movement from the baseball into my glove.
Exactly.
Okay.
Now the reflected ones, they get twice the momentum because the photon comes in and then is reflected the opposite direction.
Yep.
So it's got the same momentum, assuming it's an elastic collision.
Mm-hmm.
There's no wavelength change. So the momentum coming in is equal to the momentum going out, which is a 2 times momentum change.
Yep.
So it gets a 2 there. So
Yeah.
the add up of all the photons is the total number of photons times the percentage absorbed times p plus 2 times p times the percentage reflected.
I like it. I'm with you. Yep.
Okay. Then the next line, doing some rearranging of.
Oh, I see. I see. So you switched out the absorbed for. Okay, here it is. So it's the absorbed. If I solve this equation for absorbed, I move absorbed to the left, move reflected to the right, so I get 1 minus reflected. And so that's what you did here. It's 1 minus reflected, and then you distributed this p in. So it's p minus rho reflected times p. Okay, I'm with you.
Yep. And next line, some more rearranging. Factor out a p.
Factor out the
and
p.
Combine like terms.
You get 1
which gives 1 plus rho reflected.
Because one of them cancels. Okay, I like it.
Yeah.
Okay.
And also, we said n divided by delta t is equal to little n. So the total number of photons incident in a particular time divided by that time is equal to the number of photons incident on the solar cell per second.